Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. This is the first lecture of session 11 that is about estimation. In this lecture, inshallah, we will cover the following questions. How do we compute percentiles? And before that, of course, what we mean by percentiles. How do we estimate the value of a parameter? And why do we need the bootstrap method? How does it work? And why does it work? That's what we will cover, inshallah, in this lecture. Let's start with percentiles. So what do you mean by a percentile? Given values in a data set that are numerical, we can sort these values in increasing order. Once we do that, the values will have what we call a rank order. So we can know which value is at rank 1, which value is at rank 5, and so on. Given that, a percentile is the value at a particular rank. So for example, the 80th percentile of a collection of values can be the value at the rank that is corresponding to 80% of the values of the array or the collection, given that it is sorted in increasing order. Or more formally, it is the smallest value in the collection that is at least as large as 80% of all the values. Let's see an example that will show us how it is computed. Let's say that we have this array 17395 and we want to get the 80th percentile. So the first step to do that is to sort the values in increasing order. So we'll have the array then 1, 3, 5, 7, 9. That's the sorted order of this array in increasing order. The second step is to determine which rank we should look at. Given that we want to get the 80th percentile, then the rank is 80% of the total number of the values in the array, or the size of the array. The size of the array here is 5, so 80% of 5 is 4. So the 80th percentile is the first value on the sorted list that is at least as large as 80% of the elements in the set, which in this case will be the fourth element, which will be 7. So the 80th percentile in this case for this array is 7. Okay, so we sorted the values first in increasing order. We determine the rank by the percentage, and we look at the rank, we look at the value at that rank. Okay, which will be at least as large as 80% or whatever percent we want of the values in the array. Now you might wonder, what if the percentile that we want doesn't exactly correspond to an integer rank? So for example, if I want to get the 50th percentile in this array, 50th percentile means that 50% of the values, so the rank in this case will be 2.5. 50% out of 5 is 2.5. So in this case, based on the definition, we want to get the value that is at least as large as 50%, which means that we will take the next greater element in this case. So for the example that we have now, it will be 5, because 2.5, the largest integer to it, the next greater integer to it is 3, so the value of the 50th percentile in this case will be 5. Okay, so if the rank is integer, then we'll get the value immediately. If it's not, then we will get the next one, and that will be the needed percentile. In the data science package, there is a function that can compute that for us. It's called percentile. So percentile takes two parameters, p, which is the percentile that we want to compute, and the arrays, the values in an array. Okay, so p of course has to be between somewhere between 0 and 100, and it will return the pth percentile of the array. And it uses the same definition that we just mentioned, which is that the pth percentile is the value in the set that is at least as large as p% of the elements in the set or in the array. Let's see a quick demo on percentiles to make sure that you understood what we just discussed. Let's say that we have this array. It has 6 values, array X, and we want to compute the 55th percentile of that array. So let's do that manually first. The first step is to sort the array. So if we sort the array, we get by default the array in increasing order. So the second step is to compute the rank that we want to look at. So the rank will be 55 over 100, 55% of 6. What is 6? 6 is the size of the array, the number of values in the array, which is 6. Now this rank is 3.3. Okay, so of course there is no value at rank 3.3 because the rank has to be integer. So we will get the next one, which is at rank 4. But remember that the arrays in Python starts from index 0. So we actually need item number 3, which is at rank 4. And that will be the 55th percentile of that array. Of course, alternatively, we can just use the percentile function that will give us the same value. I just did that to show you how you can do it, or to understand how it is actually done. Okay, so that's how percentiles are computed. Here is a discussion question that I will leave for you to do at your convenient time. Given this array, which has 5 values, the same array I think that we discussed in the previous example, which of these statements are true? Percentile, the 10th percentile is 0, the 39th percentile is equal to 40th percentile, 40th percentile is equal to 41st percentile, and 50th percentile is 5. So which of these is true? It can be one answer, it can be 0, it can be more than one answer. Okay, so do it and check it with me later. Now we will shift our discussion to the main topic of the lecture, which is estimation. So what is estimation? We want to estimate the value of an unknown parameter. Okay, so we are actually given, we have a parameter and we want to get an estimate or an approximated value of that parameter because that parameter is actually unknown. For example, I want to know the average number of sleeping hours of QU students. Okay, so that's unknown to me. I want to estimate it. How can I do that? So that's the topic of this lecture and also the next lecture of this session, inshallah. Now, if you have the whole population, if you know for every QU student what is the average number of sleeping hours for the student, then we can calculate that parameter and we are done, right? If we know that value for every student, for every member or every individual in the population, then we can compute the parameter and we are done. But of course, that's not always easy. Okay, so if we don't have the population, then the solution is to take a random sample from the population and use a statistic or compute a statistic to be an estimate of the parameter. So we'll take a random sample from the population, maybe survey some of QU students and get their numbers, okay, and compute the average of these numbers. So that will be a statistic that is an estimate of the parameter. Okay, now let's do that in a demo and see how we can do this estimation. So we'll work here. Let me zoom in. We'll work on a data set that is from San Francisco State in the US in 2015. There is a data set of information about the total compensation of all the employees in the state. So in this data, we have a row for each employee with his job and his total compensation, along with other information that we just ignored for this demo. So that's the entire data set. It has about 43,000 employees. Now we'll just filter some of them that are not even a part-time or half-time employees. So the total compensation of them is less than 20 hours per week. So we'll just filter them out and focus on only about 38,000 employees. Now we'll assume that this is the population. Okay, so just for the purpose of this demo, we will assume that we have the population, which is true. We have, in this case, we have the population, but we will just try to estimate we want to get here the median of the salary, of the total compensation. So although we have the population and we can compute the median directly, but just because we are trying to show how the estimate can be different from the actual parameter, we would just assume that we don't know the population. Okay, let's compute the median of the population. Okay, so the median is at 50th percentile. We can of course use the NumPy median function, but here, since we know about percentile, it will be the 50th percentile in this case. So the median of the population in terms of the salary or the total compensation is about $107,000. Okay, so that's the median of the population, which is the known value of the parameter. So that's the value of the parameter that we want to estimate. Okay, so now we assume that we don't have the entire population, and we'll try to estimate this value to give an approximation of that value. How we can do that? We will have to get a sample, a random sample of the population. So we got a sample of 300 employees of that data set without replacement. So that's our sample. This is the 300 rows from that's just a random sample from the population, and we will compute the median for that population, for that sample. So percentile 50th percentile of that sample will give us an estimate of the median of the sample, which should be an estimation of the actual median of the population. So the sample that we got has a median of 105K. Okay, so what do we notice from that? First, we notice that there is of course a difference between the actual value of the parameter and the estimated value that we have from the sample. Okay, so that's the first thing. The second thing, which is really a problem, is that this is an estimated value out of a sample of 300 employees. Now, if we change that sample, we might get a different estimate, of course. So let's do that. Let's get another sample and recompute the median of it. So in this case, we got 108. Okay, so of course it's different. So how can we know that? How can we know the variability of the estimate? How can we know how different the estimate can be if we draw different samples? So that's a problem that we need to think about. Let's get back to the slides and talk about the variability of the estimate. So one sample means one estimate only. Okay, but of course, as we said, the random sample could have come out differently, and thus the estimate could have been different, and that's what we actually saw from the code. One sample means one estimate, another sample means another estimate. So the question is, how different could be that estimate if we changed the sample? Why is that important? Because the variability of the estimate tells us something about how accurate the estimate is. If most of the values of the estimate from different samples are very close to each other, then that will give us some quality or some indication of quality of the estimate, as we will see later inshallah in this session. Let's get back to the code and see how we can characterize this variability. So what we want to do is to compute the estimate from different samples of the population. Okay, so to do that, we'll first generalize the sampling and the computation of the statistic that we did before in a function called generate sample median. So this function will sample without replacement from the original population. Remember that the original table is San Francisco, SF. We get the sample and we return the median of that sample, okay, which is the 50th percentile. So that's the function. Now let's draw one sample from that function that gave us 106K. Now, of course, we can, because we know in this demo the actual median, we can compute what we call the error between the estimate and the actual median. So the error is the difference, which in this case is 836, which means that our estimated median is less than the actual median. Now let's repeat that multiple times. Let's repeat the getting a new sample and then compute the statistic from it. We'll do that 1,000 times, and then we plot the histogram. So here is the histogram of the sample medians, and this is the population median that we, of course, in real life we don't know it, but for the purpose of the demo we know it. So what does this histogram tell us? It tells us that the estimate that we compute from a sample can be different across different samples within that range. Okay, most likely. Okay, so it goes from maybe 90K to up to 120K. Okay, so that's how variable it is. Remember that this is from samples of size 300 out of how many we started with? We started with about 38,000 employees. So that's a very small sample. 300 out of 38,000. So less than even 1%. Okay, so this is how different the sample medians can be if we changed the sampling, if we changed the sample. Okay, so every value in the array that we computed here, the sample medians, comes from different sample. Okay, so this is how variable can be the estimate if we change the sample. Now, what is the problem with that? So of course we can see now it captures, or it includes of course the actual value of the parameter, which is the median of the population. Now, what is the problem with this method or this process? We computed the median from a sample. We repeated that multiple times, which means that we get another sample, compute the median, third sample, compute the median, and so on, and then we display the histogram. What is the problem with that? Let's get back to the slides. The problem is that we need to know where or how we can get another sample. So remember that we started by a sample, and we said that to get a sense of how variable the estimate from that sample can be, let's get more samples. So to get many values of the estimate, we needed many random samples. Why is that a problem? It's a problem because we can't go back and sample again from the population. It is very time consuming, and it is also expensive in terms of money. So what we did, although we could do it in the demo because we have the population, but in reality we cannot do it. So this is impractical. We cannot in reality go and take multiple samples from the population. So maybe we are stuck here. We cannot move forward because we cannot get more samples. But data scientists actually have another solution, which is the bootstrap method. So the bootstrap method is a technique for simulating repeated random sampling. What does that mean? What we have originally is one sample. Okay, so we will take one sample from the population, whatever the size is. We'll talk about the implication of the size later, but let's say that we have one original sample, which is large and random. So large, of course, large enough. We mean large enough. Okay. Do you remember earlier in the course that we said that if we take a large sample from the population, as the sample is large enough, it will resemble the actual population. Okay, so we'll assume that the sample here is large enough. Okay, not of course to the size of the population, but it is large enough. We'll talk about the sample size, as I said, later in the course. Actually, I think the next lecture, in the next session. Okay, so we have the original sample, which is large and random, and because it is large and random, it probably with very high probability it will resemble the population. It will be similar to the population. And then we will sample at random from the original sample. Okay, how is that different from what we have just done in the notebook? What we have done in the notebook is that we got different samples from the original population. Okay, from the original population. But in the bootstrap method, we resample at random from the original sample. Okay, not the population. Remember, we have the population, we got one original sample. Then in this method, we will resample from that sample, from the original sample. Okay, now when we resample from the original sample, we have now multiple samples. Now we can get the distribution of the estimate from the values that we compute for the estimate from each of these samples. Now, why the bootstrap works? Why does bootstrap method make sense? Okay, we have originally the population, right? We have the population, or yes, there is a population, okay, but of course we don't have the values of the population so that we can compute the actual parameter. But from the population we get a random sample, which is the original sample that we will work on. From that sample we resample to get more samples. Okay, so notice that this original sample comes from the population, and these samples come from the original sample, from the one sample that we have from the population. Now, if that sample is large enough and random, then it will be similar with high probability to the population distribution. And since these samples are coming from that sample, they will also, with high probability, be similar to the population, to the distribution of the sample, and thus of the distribution of the population. Okay, so that's the idea of the bootstrap method. We have an original sample, we resample from it, and thus we will have multiple samples that are with high probability similar to the original population. Okay, so all of these look pretty similar. If you look at the graphs here, the histograms, they look pretty similar, most likely, with high probability. So this is what we wish we could get, but we don't have. Remember, we don't have the distribution of the population, but we are still interested in computing some parameter out of the population. And this is what we really get. We get the sample, and then we resample from it multiple samples, and with high probability they will be similar to the original distribution of the population. So this is what we wish we could get, and this is what we really get in the bootstrap method. So the key to resampling is the following. From the original sample, we draw at random with replacement as many values as the original sample contained. Okay, so let's try to understand this. We have the original sample. We will draw from that randomly with replacement with as many values as the original sample contains. So if the original sample has 300 values, we will draw 300 values from that sample with replacement. Now let me first explain why we need as many values as the original sample contained. That's because we want to compare the new samples with the original sample. We cannot compare these samples, or we cannot compare the estimated values of the parameter coming from these samples with the estimate of the original sample unless they are of the same size. Okay, so the new samples have to be of the same size of the original sample. Now, if we draw at random from the original sample with the same size of that original sample without replacement, we will get the same sample. Okay, so it has to be with replacement. It has to be with replacement, and that's because we need them to be different from the original sample. Okay, so the deal is we will get the original sample, we will resample from it the same number of values in that original sample, but with replacement. So the size of the new sample has to be the same as the original one so that the two estimates are comparable. That's what we just mentioned. And now let's demo the Bootstrap method. So let's first look at the population data. So the distribution of the salaries across all the employees that we focus on. So here is the distribution of the population, just to get an idea how this will be similar from the samples or not. So this is the distribution of the population, and here is also the distribution of the sample. So we'll get the original sample. We assume that we are getting now a sample from the population, 300 employees without replacement, and we compute the sample median. Now here is the histogram for the original sample, and you can look at both. Let me make it more clear. If you look at the two distributions, they are kind of similar to some extent, although this is just a sample of 300 employees, and this is much more than that. As we said, I think 38,000 or so. So that's the original sample. Now the Bootstrap method will require us to resample from that sample multiple times. So let's try one sample. So we'll get a boot sample, which is just a sample, a random sample from the original sample, which we call it here our sample. When we just call the sample function without specifying the sample size, it will sample as many as there are in the table, and the default will be with replacement as we want. When we do that and display the histogram, we will get this one. Okay, so that's one sample, one Bootstrap sample from the original sample that we got. So also it's of course different, but it's not very different. And more importantly, it has some similarity with the original population, although again it is just a resample from the original sample from the population. Now we need to repeat that multiple times, and here is also the estimates that we got. This is the original value of the parameter, of course, the 107k, and this is 105k. This is the median of the original sample, which of course is different, and this is the estimate from the resample, from the Bootstrap sample that we got. Okay, of course also it is different. So we'll repeat that multiple times. We need to repeat that multiple times. To do that, we have to define to generalize the function. So we put that in a function, one Bootstrap median. It will get a sample from the original sample and compute the median of it and return the median. Okay, so that's the function. we need to call that multiple times, or we need to do that multiple times. So in that code now, we will repeat over this process 1000 times. We call the function to get a new median, and we add it, of course, to the array as we used to do. The one bootstrap median process is to resample. So this is resampling. Okay, let me make it clear here. Resampling. And getting the median of the bootstrap sample. Okay, so we'll run that 1000 times, and we plot it. So that's the distribution of the samples that we got. Okay, so what are we seeing here? So this is a different distribution than the ones that we saw before. The ones that we saw before were the distributions of the salaries out of the samples that we get. This distribution now is the distribution of the medians that we got from the resampling, from the bootstrap method. Okay, and the red value here is the median from the population, and the blue one here is the value from the original sample, that from which we resample. Okay. Now we can see that now we can see an empirical distribution of how the estimated median will be different if we have different samples. Okay, this is different from the one that we got earlier in the lecture, because the one that we got earlier in the lecture, we had samples from the original population. Here we have samples from the one original sample that we got from the population. Of course, we can now think of whether this is have any indication about how good the estimation is, looking at the distribution. But what we can also do is to look at the how many values are in that distribution that is in the middle 95% of the values. So what I want to do now is, among the 1000 values that we got in the resampling, I want to see how many are in the middle 95%. Or in other words, I want to get the 2.5 percentile and 97.5 percentile, and I want to get this interval. So I want to see what is the 95% interval that include 95% in the middle of the values of the estimates that we get from the bootstrap samples. So we got the 2.5 percentile and 97.5 percentile, and we will just plot it on the same distribution. Okay, so this is the same distribution, but now we will see that interval. Okay, so that's called 95% interval of the distribution, which means that it is in the middle of the entire distribution of the values. Okay, and we can see that this interval, of course, includes the original value, or the value of the parameter, okay, which is the red point here. This interval is called, and we will see why in the next lecture inshallah, is called 95% confidence interval. In the next lecture inshallah, we will know, or we will answer the question why we call it confidence interval. But at least in this lecture, we can see that it is an interval that has 95% of the values in the middle of the distribution that we got from the bootstrap method. Inshallah, next lecture we'll talk about confidence intervals. See you, or talk to you inshallah in the next lecture. Assalamu alaikum wa rahmatullahi wa barakatuh.